Thanks, Yang. Thanks for the organizer, Brian Yang, for inviting me. So today I'm going to talk about a project we recently finished with Uri, and the paper is coming out in a few weeks. So the study is about compression of morbidity by interventions that steepens the survival curve. Come back. Don't know how to use this. Can we start from the beginning? Okay. Okay, now I get the gist of it. So important criteria when people try to think about longevity interventions is what we call six-span, which is the period of life at the end where you suffer a lot from age-related diseases and functional deficits. So important criteria when you consider longevity treatment is what's your effect, not just on lifespan, not just on health span, but what's the effect on six-span. So for example, consider an extreme scenario where we don't do anything about aging, but just keep everybody alive at the end of life for longer. So you'll get increased lifespan, you'll get nothing on health span, but you get a much longer six-span. And that's bad news for the individual and for the society. An alternative scenario is we are able to have a hypothetical treatment that slows the rate of living. And here we'll get proportional increase in health span and in six-span, so that's better. But what's even better is that if you can find a treatment that increases lifespan and all the years you gain are in health span. And proportionally speaking, you compress the six-span. And in fact, this is proposed by James Fries and Kenneth Menton in the 1980s to be the optimal trajectory of aging. But in order to bring this into real life, we have to have data. And to measure six-span or health span, what you need is longitudinal health data, and especially under interventions. And this is relatively rare. So what we did is we considered some data that are much more widely available. This is the survival curve that Uri introduced. So this curve is almost always published when some new intervention is described. And people usually consider longevity intervention if the median lifespan is extended. However, this curve actually carries much more information than the median. So we want to consider the shape of the survival curves. So here I'm showing you two real-life longevity interventions in mice. You'll see what they are later, but I won't tell you what they are for now. And the top row is what we call a scaling intervention. So you'll see in the top left that the median lifespan is extended, but when we normalize the x-axis by the median lifespan, we see that the two curves collapse onto itself. So the shape of the survival curve is preserved by this intervention. In contrast, in the bottom row, you also have a longevity intervention, an increased median lifespan, but when you normalize the two curves, they don't collapse onto each other, and the red curve, which is treated, is steeper than the control curve. So this is what we call steepening intervention. So now I'm very happy to follow the talk of Uri because he introduced all these models, so I just be quick. So the model is based on a simple assumption that there is a dominant kind of damage that drives both morbidity and mortality. And we try to model the dynamic process where damage is produced and removed. And in these two separate studies, we modeled the damage trajectories of individual mice and individual E. coli. And we found the same unifying circuit that governs the damage process, which is that the damage production increases with age linearly, and that damage removal saturate at high damage levels. And if we simulate this model in the computers, we'll get these kind of stochastic trajectories of damage. And if you assume that the individuals die when the damage crosses a certain threshold, we'll get a lifespan, but each individual die at a different time. So this gives us the survival curve. So now if we, in the computer again, modify the damage production rate by decreasing it, we'll get longer lifespan. But our model gives us a longer lifespan, but scaling survival curves. So you have the same shape, but longer lifespan if you change damage production. So in contrast, if you change the other parameters in the model, what you get is always you can get a longer lifespan, but you almost always steepens the survival curve. And if you quantify the steepness of survival curves by dividing the mean lifespan by the standard deviation, we can plot each survival curve on the 2D axis. So on the y-axis, we plot steepness, and on the x-axis, we plot the median lifespan. And we always compare a treated group to a control group. So you get relative effects on both steepness and longevity. And we see that the 4 kinds of interventions reside in different regions in this plot. So imagine that you have a real-world longevity intervention, and you quantify lifespan steepness. You can put your intervention on this plot, and you are able to identify which biological process the intervention operates through. Now, we're interested in six-span. So in our model, we can also model morbidities and functional deficits. So in this paper, we cited here, Kathir and his co-authors modeled hundreds of age-related diseases with a simple threshold that's lower than mortality, we called XD. And once damage crosses threshold, we consider the individual to be alive, but starting the onset of some age-related morbidities. So the six-span now is the time it takes for damage to travel from XD to XC. So now if we simulate the model again for hundreds or thousands of individuals, we get this kind of longitudinal plots, where in each row we plot the health span, six-span, and lifespan. So this is our control group. So the relative six-span is at 14.5%. And again, if we decrease the damage production rate, we get a scaling survival curve. So the survival curve looks almost exactly the same. And the relative six-span is slightly increased, but almost the same. So this is relatively easy to understand because in our model, the only place where age enters into is in damage production. So if you change the effect of age, it's like you're stretching a rubber band. So you're stretching both the lifespan and the six-span. So that's why the relative six-span is roughly the same. Where in contrast, if you increase the damage removal rate, what you get on the bottom left is the steeper survival curve, as you've seen before, but also you can notice that the six-span is compressed, reduced to about 10.5%, given the same magnitude of lifespan increases. In fact, if we try all the parameters in our model, almost all of the steepening interventions results in compression of six-span. The only exception is this green curve you see at the top, where we're keeping the disease thresholds constant, but increasing the death threshold. So this is equivalent to the artificial sustainment of life scenario that you've seen in the first slide. So this result is actually also intuitive to understand, because by either increasing damage removal, decreasing noise, or increasing the morbidity and mortality threshold, what you're doing is mitigating the effect of this stochastic damage. So what you end up with is that you're both delaying and homogenizing the onset of morbidity and mortality. So now we've seen that in SR models, steepening interventions will compress the six-span. So what about in real life? So the short answer is this relationship holds in real life. So I will walk you through each panel here in this section. But in general, what you're seeing here is 4 studies where we have longitudinal health span data under interventions. And we plot the steepness on the y-axis and steepness on the x-axis. And each marker there is an intervention, consists of a control group and an intervention group. And what you see here is that the relative span decreases with steepness as predicted in all cases. So the first study we consider is from mice, where Luciano and her colleagues measured longitudinally every weekly the frailty index of 6 groups of mice. And what they do is they consider the 6 span to be the period of life with 4 or more deficits. And we kept this definition, but also tested alternative definitions. And under all alternative definitions, 6 span decreased with steepness. Next, we consider Drosophila. And in Drosophila, this group of authors from Greeks measure longitudinally local motion deficits. So what they do is they bend the vial that the fly is living on the counter to startle them and measure their ability to fly, to jump, and to climb. And they quantify the deficits in all these local motion functions and plot this beautiful data and shared with us the raw data. So we analyzed this data of 2 Drosophila strains under 6 dietary conditions for both sexes. And the result is still consistent with the model that the relative 6 span decreased with steepness. And lastly, we consider C. elegans, where we consider 2 separate studies where they define 6 span differently. So the more common definition is by voluntary movement. So if the worms stop to move, they consider them to be sick. But this criteria is often debated because whether they are able to move or whether they are willing to move are 2 different questions. So Statzer and his co-authors developed a microfluidic device where an electric field forces the worms to move and they can measure their maximum muscle strength. And under these 2 definitions of 6 span, 6 span decreases with steepness as well. We also vary the definition of steepness in our study. So steepness is just a dimensionless measure of the shape of the survival curve. So we're able to use different definitions of steepness by using not just the standard deviation and the mean, but also the quantiles as well. And in all the definition we tested, this negative relation between steepness and 6 span is robust. So next, we want to apply our theory to identify interventions that can compress the 6 span. So here we considered all the interventions in the NIITP program, where this is a fantastic open experimental investigation systematically of mice interventions, and they publish all their survival curves. So what's plotted here are all the interventions that we consider to be not significant. They didn't pass our statistical thresholds. And you see that all these dots lie around the origin. And the very well-known group of interventions, which are calorie restriction and rapamycin, what we see is that they do prolong lifespan significantly, but they do not change steepness significantly. So they are what we call scaling interventions. So rapamycin and calorie restriction are scaling interventions. In contrast, there are about 4 groups of drugs that increase the steepness of survival curves. So these are alcohols, BD, which simulate the effect of ketosis, 17-alpha-E2, which is a non-feminizing estradiol, and captopril, which is an ICE inhibitor that improves the vasculature. So for all these 4, we predict that they were able to compress the 6 span in their respective genders. We also scanned the literature to find 26 additional interventions that are not not published in INITP. So there are 2 more classes of interventions, which are VEGF overexpression and senolytic drugs or senolytic drugs that kill senescent cells. So under also these 2 classes of interventions, we predict that 6-span would be compressed in mice. So the next application of our theory is on combination of interventions. So the core idea is this. If we're able to pinpoint what biological process a given intervention operates through, then we should be able to find interventions that operate on different biological processes. And if they operate on distinct biological processes, they should act independently and additively. So as you've seen before, rapamycin are a scaling intervention. So we think that they operate through damage production. Whereas uncables, we identified it as a beta intervention, which means that they increase the damage removal rate. And because these 2 drugs act on distinct processes, they should act additively. And indeed, this is the case in the data. So again, we plotted both the single interventions of rapamycin and uncables and also the combination interventions on the graph of steepness versus longevity. And you can see that the theoretical curve, which are the dashed line eclipse, so that's the confidence interval for the additive model, is consistent with the experimental data. So this is just one drug intervention. So if you have more drug intervention data on either lifespan or performance, perhaps we could collaborate and further test this idea. So I would like to thank my co-authors, Toma and Avi and Danja Roche, who are not here, and Ben and Nave, who are here, and of course Uri. And I would also like to thank Dr. Consulas, Ham, and Strusu, who shared their data in flies and worms with us, and members of the Alone Lab and outside of it that contributed to this work. And lastly, I would like to pitch my own research group that's having started for 2 months at the Westlake University in the beautiful city of Hangzhou, China. And we're recruiting PhD students and postdocs to do exciting projects in systems aging. Thank you.
Thank you for the great talk. So it seems to me that an additional way to validate your model would be to put some actual biology on the removal rate versus the production rate. So do you have any ideas on what these could be, biologically speaking, how they could be measured, and do you agree that this would go a step further into validating your model?
Thanks. So that's a very interesting question. So just by using the result we currently have, which are interventions, we already start to understand what the biological process is. For example, if the alcohols affects the removal rate, then we understand maybe the removal rate has to do something with blood glucose-induced problems. Same with VEGF. So if VEGF increases the removal rate, then perhaps the removal has to do with the blood vessels. So this is one way we can understand the biology behind these processes. The other is, of course, use genetics. And there's much more work that can be done with genetics using the same methodology.
Thank you.
Great talk. I love the approach and completely agree that we need a lot more intervention data to test and validate these kinds of models. My question is whether there might be opportunities to build in functional data in addition to the survival. And I'm thinking specifically with rapamycin, which you characterized as a scaling intervention, doesn't compress 6-span based on the model, yet we know from the functional data that you can take aged mice where there's already been functional declines, start treatment with rapamycin, and you see improvements, right, which would suggest there is actually something going on with 6-span. So I wonder if there's a way to kind of build in. I'm thinking like with rapamycin, we can see improvements in heart function, brain function, immune function, reversal of periodontal disease, and others. So is there a way to build in that sort of data to refine and make the models reflect what seems to be improvements in health span?
Mm-hmm. So that's also, again, a very interesting question that perhaps gives us ways to go forward. So for example, the drug combination idea. That's just the mechanistic insight by using mortality data, but we don't have to stick with mortality data when it comes to predictions. We can, so if they act mechanistically independently, then if they should act additively even when it comes to performance data. So same with like shifts. So I didn't discuss what happens when you apply rapamycin in shifts. So I think this will be a very fruitful directions, and we are kind of limited with what kind of data we're currently using. So more data would sort of not only validate the model, but also finding where the model is lacking and improve on it.
Cool, thank you.
Okay, thank you for the great talk. As I know, the saturated removal model returns specifically the first passage time statistics of saturated removal model returns Gompertz-like statistics. And we know that Gompertz distribution has two parameters, A, constant mortality, and B, that refers to rate of mortality. My question, and your result, and specifically the steepness coefficient, is very similar to the relation between mortality rate and constant mortality. Did I correctly understand that steepness coefficient actually reflects the relation between those two coefficients in Gompertz model?
So the question has to do with steepness relationship with Gompertz slope.
Steepness coefficient is the same that the relation between B and A coefficients in Gompertz statistics.
Right. So that's also a good question that we asked by reviewers. So if the survival curve is purely Gompertzian, which in the case of mice is not, but if the curve is purely Gompertzian, steepness corresponds to the Gompertz intercept, and scaling changes correspond to changes in the Gompertz intercept. So for example, humans are almost Gompertzian, and so far we haven't seen anything that can change the Gompertz slope. So in humans, it's hard for me to imagine to have scaling interventions, but there's a part in our paper about humans that we said that human curves have been steepening, and that's mostly due to external hazard. So I hope that answers your question.
Yes, thank you.
Hey, thank you for the talk. My question is, what is damage? Every change is damage or not? And what do you think damage should increase mortality, or there can be damage that is not increase mortality in long term or short term?
So the question has to do with what is damage, and is that the question?
Yes.
So because we tested this idea in different organisms, so in different organisms the answer might be different. And we are kind of agnostic towards what exactly is damage, and this needs further investigations, like what Uri introduces in his talk. But this idea should hold regardless of what is damage. It matters how noisy is damage and how this noise level is regulated, but it doesn't really matter what exactly the nature of damage is.
Okay. Thank you.
Hi. Thank you for your talk. It's lovely to see the survival curves being mined for insight. The question is the sex differences. It looked like there were some systematic male-female differences, for instance, in steepness effects in interventions. Can you comment how significant they are and how you interpret them?
Right. So the question has to do with sex differences in steepness, and the answer is, so we did have a part in the paper about that. So in mice, and I think it's also true in humans, that females are steeper than males. And the other thing is that we're more likely to have steepening interventions in males, perhaps because we're not as steep as females, so there's more space for improvements.
And that was, I saw it in the mice and the flies. You're saying it's also in humans?
Yes, it's true that human female curves are steeper than human male curves.
Thank you.